we are discussing about Crammers theorem. So Crammers theorem means limit of 1 by n log of maybe log base e probability that Sn by n is greater than a. So this quantity we determine that is equal to minus L of a. This is the Crammers theorem we want to prove. We have already established that 1 by n log of probability Sn by n greater than a, that is less than equal to minus L of a. So that is the upper bound, logarithm of this probability divided by n, it is bounded by minus of La. Next we will establish the lower bound. So what we will establish lower bound for 1 by n log of probability that Sn by n greater than a. So what we will show that as under limiting condition as n tends to infinity, this quantity is greater than equal to minus of La plus epsilon. That means if we have somewhere, suppose this is minus La, because La is a negative quantity, so that way we will get minus La, and this term is suppose minus La plus epsilon. So what we will show that this quantity is greater than minus La plus epsilon, minus of La plus epsilon, where epsilon is an arbitrarily small number. So we want to establish this. For this we consider a new sequence of IID random variables. So yn is a new sequence. How do I get this? We obtain by mapping xi to yi such that probability density function PDF of yi is given by this relationship. Fy of y, that is PDF of any yi, if we consider, PDF will be transformed by this relationship e to the power s star y. S star we know this is the point where this rate function is computed, divided by mx of s star into fx of y. This is the relation between fy of y and fx of y. At a point y, the relationship between PDF of x and PDF of y is given by this. Now this way we define a sequence yn, which is a function of independent sequence xn. So that way this will be also IID sequence, and our aim is to find out the MGF, moment generating function of y. So we can apply the definition. Then what we will do is we will substitute fy by the quantity which we have defined earlier, that is in terms of the PDF of x. So we get this quantity, and ultimately here it will become e to the power s. So this term will be becoming e to the power s plus s star into y. So because of that, now this MGF of y will be given by my of s, that is related with the MGF of x by mx of s plus s star divided by mx of s star. So this is the relationship, that is mys is given by this. Okay. Now because of that, now we have to find out suppose what is the mean of this distribution. That is important, we have to use that. So we immediately find out that u of yi, IID sequence, this expected value EYI, that is equal to the derivative of the MYS, that is MGF at y is equal to 0. So if I take the derivative of this will be simply mx dash of s plus S star, and this is not a function of S. So that way we will have only this quantity differentiated, and when I put S is equal to 0, this is mx dash at S star divided by mx of S star. So that is equal to A, and we know that from the relationship that AS minus log of mx of S. So we use this symbol for log base E. Now this one, when we find out the relationship that what will happen at the maximum, so then we find out the derivative and then equal to 0, then we find that this quantity mx dash of S star divided by mx of S star is equal to A. So that way what we have established that yi is an independent and identically distributed sequence with mean E of yi is equal to A. Now let us see what happens to the sum of this sequence, yi sequence. So Sn tilde, let us call this is the summation of yi I going from 1 to n. Now MGF of Sn tilde will be given by this, and this is nothing but mys to the power n because of the IID property. And I know what is my of S, that is mx of S plus S star divided by mx of S star, so to the power n. So that way, and also I know that this quantity is the MGF of Sn. So that way MGF of Sn bar will be equal to MGF of Sn at S plus S star divided by mx S star to the power n. So this is the relationship we get. So now we can use this relationship to find out the PDF of Sn tilde. So we have already established this relationship. So if I apply the definition of MGF, then this quantity, left hand side quantity will be this e to the power su f Sn tilde u du, and this quantity right hand side if I write, then this will be e to the power S plus S star u into f Sn u du divided by this quantity. So now if I consider the integration with respect to du, and if I take e to the power su into e to the power S star u here, if I write here this quantity as e to the power su into e to the power S star u, then I will have an expression e to the power su multiplied by some quantity into du, that e to the power S star u into f Sn u divided by mx S star to the power n, that quantity will be now f Sn tilde of u, because left hand side if I compare with the right hand side, I can establish this. So what is the aim? We have found out the PDF of f Sn tilde, PDF f Sn tilde in terms of the PDF of f Sn, that is f Sn u into e to the power S star u divided by mx of S star to the power n. So this is the result we have established. Now let us see how to find out the probability. Our interest is to find out this probability that Sn greater than Sn by n greater than a, which is same as probability that Sn greater than Na. Now we can write this as from Na to infinity f of Sn u du. So this probability is in terms of the PDF we can write, this is from integration from Na to infinity of f Sn u du. Now this expression I can write, okay. So I can write this is this PDF of Sn is given by PDF of Sn tilde into this quantity. So that way we can now determine this probability in terms of the probability involving f Sn tilde u. We have already told that this quantity is equal to integration of this quantity from Na to infinity. Now we can do two things. If we instead of infinity, if we write some Na plus n delta, because it is Na, this is Na plus n delta, delta is a small quantity, then this integration, if I instead of infinity, if I put upper limit as Na plus n delta, then this quantity will be greater than this expression. Okay. So that means if I write this limit as Na plus n delta, then we will have a greater than equal to sign, and this is the first thing we will do. And second thing, for e to the power star u, we will put this smallest one. When I put Na plus n delta, this quantity will be smallest, so I can put that quantity. So therefore it will be still greater than equal to e to the power s star n into a plus delta mx of s star to the power n, and then integration of f Sn tilde u du from Na to Na plus n delta. So we can now write in terms of log, so that we will have a quantity now e to the power minus s star Na n log of mx of s star and minus s star n delta. And this quantity, we observe that this is the probability that Sn tilde lies between Na and Na plus delta. Okay. Now yi sequence, that is a sequence with mean A. So therefore Na is the mean of Sn tilde. So therefore this is the probability that Sn tilde lies between mean and mean plus some n delta. Now if we recall this quantity, now this quantity, as when n becomes large, suppose this quantity, this probability, what we can write, this is equal to probability that I can Na subtract it 0 less than equal to Sn tilde minus Na less than n delta. Now this is n delta as n tends to infinity. This quantity we can apply the central limit theorem, and this probability will be equal to half. So because this is the mean 0 of this expression, and as n tends to infinity, whatever delta is, this quantity can be made to diverge to infinity. Therefore this is the probability that Sn tilde minus Na lies between 0 and infinity. That probability is half. So therefore we establish that probability of Sn by n greater than A is greater than equal to e to the power minus s star Na minus n of log E mx of s star into half into e to the power n delta s star. Now this half we can take, suppose we can further write this expression. Suppose first we took n as a common, then here will be s star A minus log of mx of s star, that is nothing but the rate function La. So that way we get it e to the power minus La, and this term we can write it as this term. So we can write it as e to the power minus n delta s star. Now half we can write as e to the power minus log of 2. So, that way minus log of 2, and if I take n common, then I will get this as delta S star, this divided by n. Now, this quantity can be made as small as possible. This is that way this quantity will be now our epsilon. Therefore, we can write it as this probability is greater than equal to e to the power minus n of LA minus n of epsilon. So, what we establish? Therefore, as n tends to infinity, dividing by n as n tends to infinity, what we will get? So, as n tends to infinity, this quantity will become very small, it will become epsilon. We show by dividing by n and taking the limit as n tends to infinity, we show that this quantity is greater than equal to minus LA plus epsilon. So, we have the lower limit, this is the lower bound. So, we have the lower bound now. So, what we establish is that limit 1 by n, n tends to infinity, log of probability that Sn by n is greater than a. So, that deviation probability we are taking the logarithm. So, this is greater than equal to minus LA plus epsilon. So, of course, this is true for as n tends to infinity, and we have the upper bound already we established using the Chernoff inequality. So, what we have established that 1 by n log of probability that Sn by n is greater than a. So, this quantity is less than equal to minus LA. So, this is for any n. So, comparing these two, we establish that as n tends to infinity, this quantity 1 by n log of probability that Sn by n is greater than a, that is equal to minus LA, where LA is the rate function. Thus, for large n, the utility of this expression is that if we have to find out the probability that Sn by n is greater than a for large a, then this quantity will be approximately equal to e to the power minus n into LA. LA is the rate function. So, this is the result using the Crammers theorem. Now, we can find out some probability of some deviation which may be large by using this result. So, in the case of central limit theorem, we were able to find out this probability only for some particular cases of A, that is which is order of 1 by that is 1 by root n, that order was needed. But here for any big number A, we can find out this probability. That is the use of large deviation theory, Crammers theorem. So, that way we can now consider one example. Suppose xi's are Bernoulli random variables. They are so we are considering a sequence of Bernoulli random variables. So, Sn suppose is a sequence summation of xi, I is equal to 1 to n, where xi is Bernoulli random variable with parameter p. What does it mean? Xi is equal to 1 with probability p, 0 with probability 1 minus p. So, what will be the MGF mx of s? So, this is e to the power sx. So, that way with probability p, it will be e to the power s into 1, p into e to the power s, and into plus with probability 1 minus p into now e to the power s 0, that is equal to 1. So that way p into e to the power s plus 1 minus p, that is the MGF of x. Now we have to find out the rate function. So for that we have to maximize this quantity as minus log of, because MGF is p into e to the power s plus 1 minus p. So log of that quantity, as minus this quantity we have to maximize with respect to s. So for this, if I take the derivative and put derivative is equal to 0, we will get s star is equal to this. And now we can put this s star into this expression, so that we will get that rate function LA is equal to a log of a by p plus 1 minus a into log of 1 minus a divided by 1 minus p. So therefore we can find out probability of, suppose probability that Sn by n is greater than equal to a will be equal to that will be approximately equal to e to the power minus n into LA. So that way we can find out this probability, approximate value of this probability, and we also know what is this probability. We can evaluate this quantity, because I know that Sn, this is the sum of n independent Bernoulli random variable, that is nothing but binomial distribution with probability parameter p and that number parameter n. So that way this is a binomial, therefore we can find out the actual value probability of Sn by n is greater than equal to a, that is same as, that is equal to probability that Sn is greater than Na. So this now we can, using the binomial probability distribution, we can exactly find out this probability and compare with the approximate value obtained by the Crammers theorem. We can show that this bound is very tight. It is for large n, it will be almost equal to this quantity. So this is the utility of the large deviation theory. We covered one theorem, that is Crammers theorem, and that can be used to find out the approximate tail probability. To summarize, we discussed about the motivation to large deviation theory. First we said that weak law of large number, and that is Sn by n in probability, it will approach to mu. So what does it mean? That probability that Sn by n will be deviated from mu by any small epsilon amount, probability that Sn by n minus mu, absolute value of that is greater than epsilon, that probability is 0 as n tends to infinity. Therefore, we cannot find out any deviation using the weak law of large number. Similarly, we discussed central limit theorem, because here Sn by n mu divided by root 10, that is only normally distributed. And large deviation theory, what does large deviation theory? It find out the probability limit of this quantity, instead of suppose divided by root n or simply Sn by n, here we consider this quantity log of probability Sn by n greater than a divided by n. What is the limiting value of this quantity? That is equal to minus La, where what is La? La is that is maximum s greater than 0 positive s of as minus log of mx of s. Mx of s is the moment generating function of s. So that way we can find out La. We first establish this Chernoff bound. So we took the help of the Chernoff bound to establish this 1 by n log of probability that Sn by n is greater than a, that is less than equal to minus La. That is the Chernoff bound, and apply the transformation method to show that probability this log of this probability divided by n as n tends to infinity, that will be greater than equal to minus of LA plus epsilon, where epsilon is a arbitrarily small positive number. Hence, we establish the Crammers theorem. What is that Crammers theorem? Limit 1 by n as n tends to infinity, of log of probability that Sn by n is greater than equal to epsilon. We can write that is equal to what? Minus L of A, where LA we have already defined, that is the rate function. So that way we can find out this, suppose we have to find out the probability that Sn by n is greater than A, greater than equal to, also we can write. So this will be equal to e to the power minus n into LA. So this is the final result we obtain. Thank you.